didn't know till today that there's evidence from years ago that there's something there. Europa is one of the most fascinating bodies in the solar system. We think beneath its icy surface is a global ocean, twice the volume of all of Earth's oceans combined. In the late 1990s, the Galileo spacecraft explored the Jupiter system. It made about a dozen flybys of Europa. It took observations from its cameras and from its magnetometer.
By discovering that there was an induced magnetic field at Europa, we were led to the conclusion that there must be an ocean just beneath the icy surface of the moon. But there were some strange signatures in the magnetic field that we had never really been able to account for.
Images of Europa from the Hubble Space Telescope have hinted at gases that might have come from plumes erupting at Europa.
The Hubble images had given an estimate of the height and width, and I knew how fast Galileo was moving relative to Europa.
There are better tools now, better computational techniques, better computing, that we can go back and look at that old data set anew.
So my colleague Shinja Jia set up a calculation to see what would happen in the environment of Europa if there were such a plume. And when he ran this simulation, it agreed just beautifully with the data that we had collected.
Reanalysis of the Galileo magnetometer data suggests that the Galileo spacecraft, on its closest flyby of Europa, flew through a plume. The Europa Clipper mission is going to explore Europa to investigate its habitability. If we find active plumes, then we can sail on through them and sniff and taste that stuff that's in the plume. We can analyze the particles and the gases to get at the detailed composition of Europa's interior.
We are one step closer to finding out whether we're alone in our solar system. NASA announced Monday Europa, one of Jupiter's moons, is shooting water vapor about 100 miles into space. Europa is considered the best chance for life because it is thought to have an ocean of water beneath its icy surface. And if scientists can capture the vapor being shot out, they can determine if it contains the building blocks for life. NASA plans to send a spacecraft to Europa in 2022.
Scientists have been theorizing about a subsurface ocean on Jupiter's moon Europa ever since the Voyager and Galileo spacecrafts provided data that gave a peek at this icy moon. One question that has captured astronomers' imagination: could there be life on Europa? On Monday, NASA scientists reported that ultraviolet images taken by the Hubble Space Telescope in 2014 suggest there may be water vapor plumes erupting off the surface of Europa. Astronomers first found evidence of jets of water being thrown off Europa's surface and into space on Hubble images taken in 2012. Monday's results bolster those observations, the scientists say. The plumes are estimated to rise about 125 miles before raining back down on Europa's surface. The space agency scientists observed what they described as finger-like projections while studying Europa's atmosphere as the moon was passing in front of Jupiter. Europa is thought to have a huge global ocean containing twice as much water as Earth's oceans. But scientists believe that the ocean is hidden below an icy surface that might be miles thick. The scientists say that the observations made in 2012 and 2014 both suggest that the plumes may sporadically erupt for some time and then die down. If confirmed, Europa would be the second moon in the solar system known to have water vapor plumes. In 2005, NASA's Cassini orbiter detected jets of water vapor and dust spewing off the surface of Saturn's moon Enceladus. The findings on Europa are significant because the moon with its subsurface ocean is the most likely place to find life beyond Earth in our solar system, the scientists say. If water vapor is indeed venting from the moon's surface, it could mean that probes sent to Europa might be able to sample its oceans by flying through the plumes, for instance, instead of having to drill through thick ice. NASA is planning a mission to Europa that will aim to confirm the existence of plumes during multiple flybys. The scientists also say they want to use the infrared vision of NASA's James Webb Telescope, scheduled to launch in 2018, to take a more detailed look at the venting activity on Jupiter's icy moon.
Thank you very much, Bruce. This is a pleasure to be here and an honor to be here to talk about Europa, one of the most spectacular objects in the solar system. Not just because it has really cool geology, but also because there is the possibility that there could be life in a global scale ocean beneath its icy shell. This is our spacecraft, the current best representation of the spacecraft that we hope can visit Europa as soon as the mid-2020s. As I mentioned in the Q&A, we've been working for nearly 20 years to get going a dedicated mission to Europa since the discoveries from the Galileo mission showed that Europa most likely has this global ocean. So we're going to talk a little about why we think there's a global ocean, what that implies in terms of the possibilities for life. We'll look at the cool geology, and we'll talk about this spacecraft mission and what it can do toward plumbing Europa's ice shell, telling us where there's water, what the characteristics of Europa might be like, essentially whether it may be a habitable environment, and then the next steps beyond that. Here's the star of our show. It doesn't look like, it's about the size of Earth's moon, but it sure doesn't look like Earth's moon. It's not covered with impact craters. Instead, we see these bright plains crisscrossed by these weird lines and some darker kind of mottled areas, but very few impact craters visible in this image. In fact, from the number of the paucity of large impacts, here's one. That's not one, that's something else. We can get an idea of the age of Europa's surface. Europa was formed with the rest of the solar system about 4.5 billion years ago. But the surface has been repaved. From the few craters, we know one 10 to 20 kilometer crater should form about every 4 million years. So you count them all up, and you say, well, that surface must be only about 60 million years old. Something has repaved Europa since the time dinosaurs roamed the Earth. It's these ingredients for life that I want you to kind of see interwoven here as we go forward. And this is the case when we think about exploring Mars or Europa or another planetary world, does it have a solvent, like liquid water is the best one, for the kinds of chemical reactions that could allow for life? Does it have the right elements from which organic molecules could be built? A tough one is whether there is the right chemical energy for reactions that could power life, because at Europa we're not going to have life at the surface. You'll see why, but maybe there could be life in the interior ocean. And are these ingredients around for a while? If they just show up for a few years or even a few million years, that might not be enough. The moons of Jupiter were discovered in 1610 by Galileo, and so collectively they bear his name, the Galilean moons. So this is the discovery photo. And this is what we know today based on the Galileo mission, the mission that was named for Galileo Galilei, that orbited Jupiter from 1995 to 2003, and every couple of months, it would do an orbit, and every orbit it would fly by one of these large moons. And about a dozen times it flew by Europa. And we know some from telescopic observations. We know some from previous observations from the Voyager spacecraft that flew past the two Voyager spacecraft that flew through the Jupiter system. But most of what we know is from the Galileo mission. So let's take a closer look at Europa itself. I mentioned the bright plains, the dark mottled terrain. There's another crater here that's spewed ejecta across the surface of Europa. Let's look close up at that ridged plains. It's crisscrossed by these bizarre ridges and grooves and associated kind of dark material. What the heck's going on there? It's really like nothing we see on Earth. And then there are these chaotic regions, these regions where the surface is broken up, kind of like cooking hamburger on a grill or something there. The pre-existing terrain is just crumbled away. We'll take a look more closely at both of those. This is what we think we know about Europa's interior. We know this from gravity data and from magnetometry data and from putting the pieces together, what we know about how planets work and the compositions out in the outer solar system. So we can use gravity data to tell us how centrally concentrated Europa is. So as the Galileo spacecraft flew by Europa, Europa would perturb the orbit of the spacecraft just a little bit. And from that, we can actually say, oh, Europa must be denser down in its center than it is elsewhere. And if we take the assumption that what makes up moons out there is things like iron and things like rock and things like water ice, then you get a model something like this. About 100 kilometers of H2O, what's that, about 60 miles of H2O, some of which may be liquid, as we'll talk about. The best model is that the water ice shell may be about 20 kilometers, about 13 miles thick, and we'll talk about that a little bit as well. But that leaves about 80 kilometers of liquid water above a rocky seafloor. That makes for about twice the volume of all the Earth's oceans combined at little Europa, the size of Earth's moon. So the gravity data tells us that Europa is centrally concentrated. We actually know from telescopic and Voyager observations that there's ice on the surface. Why do we think there's a liquid water ocean? Well, some of that evidence comes from geology, but the best evidence actually comes from magnetic data, from understanding the magnetic field in the vicinity of Europa. So the Galileo spacecraft had a magnetometer, and as the spacecraft sailed by Europa, there was a signal that looked like Europa has a magnetic field. Oh, okay, maybe it has a magnetic field of its own. Ganymede, its neighbor, has a magnetic field of its own, so not completely crazy. But then the Galileo spacecraft flew by again, and the magnetic field had shifted, like completely turned around. So magnetic fields don't just flip on really short time scales. So what was realized, because actually Callisto seemed to be doing the same thing, is that Europa is behaving as a conductor. There's something inside Europa in the shallow subsurface that's essentially conducting electricity. It's kind of like Europa set off a metal detector. Let me explain what I mean. Jupiter has a gigantic magnetic field. if you could see it in the sky, the angular size of Jupiter's magnetic field as viewed from Earth would be about the size of the full moon in the sky. Incredibly powerful magnet. And Europa is orbiting within that. Well, Europa feels a changing magnetic field of Jupiter because of the geometry, the tilt of Jupiter's magnetic field as it rotates around. So Europa is just minding its own business, orbiting Jupiter, but it feels a changing magnetic field from Jupiter. And Europa seems to be creating a magnetic field of its own to counter Jupiter's. So back to the metal detector idea. If I take my iPhone through a metal detector, it sets it off because metal detector is like a big magnet. And if I move something metal through a magnet, it creates another little magnetic field to counter that and sets off the metal detector. So that's kind of what Europa did to the Galileo spacecraft. It said, oh, something's weird here. So that tells us there's a conductor in the shallow subsurface of Europa. Well, what conducts electricity in the shallow subsurface of an icy moon? Salty water would. And so that's the best evidence that there's an ocean within Europa, comes from that magnetic field data. We don't know how thick that ocean is or how salty. That's something we want to do with this follow-up mission, but we're pretty sure there's an ocean up in there. We'd like to confirm it. We'd like to confirm it with other data, of course. This is kind of the interior picture of Europa. Scales are exaggerated a little bit. And why would Europa have a liquid water ocean within it today if it's only the size of Earth's moon? We know Earth's moon is pretty cold and dead today. So shouldn't Europa have lost all of its internal heat by now, after 4.5 billion years, just like our moon has lost most of its internal heat? There's another source of heating out there that doesn't apply, at least doesn't apply anymore, to our moon. And that's called tidal heating, coming from tidal flexing. Europa, as it orbits Jupiter, gets a little closer and a little farther. Again, not to scale, but the orbit's a little egg-shaped, a little bit eccentric. When Europa is closest to Jupiter, it is stretched out more. And when it's farthest from Jupiter, it contracts a bit. And kind of like bending a paperclip back and forth, that generates heat. It's frictional heat as Europa is flexed. Again, not to scale, but Europa, every time it orbits Jupiter, every 85 hours, every 3.5 Earth days, its ice shell is flexing by about 30 meters. That's the prediction for how much it would flex as it goes around. That'll generate a lot of heat. Some of you may know Io, Europa's neighbor, is the most volcanically active body in the solar system. That's the moon 1N, the Galilean moon 1N from Europa. It flexes something like 100 meters. It's crazy to generate all that heat at Io. Well, a little farther out at Europa, it's not enough to make a super volcanically active body, but it's enough, we think, to maintain a liquid water ocean. And you do the math and you say, okay, it makes sense for the ice shell to be something like 20 or 30 kilometers thick above an ocean, in turn above the rock. We don't know how much of that tidal heat is in the rocky part of Europa. If the tidal heat is just in the ice shell, that's enough to maintain an ocean. But it could be that there's a bunch of heat put into the mantle as well to keep it warm and for there to be volcanoes down on the seafloor of Europa. We don't know yet. So something else we want to do with a mission is we want to test for this flexing. We want to fly by Europa when it's at different places in its orbit and measure the gravitational field very precisely. And by doing that, we'll be able to infer how much it's flexing and to nail in another way the idea that Europa has an ocean down there. All this tidal flexing kind of breaks the surface too. And so when we look at pictures like this of Europa, we're zooming into some of the highest resolution Galileo data here. That may help explain these ridges and cracks that crisscross the surface. Although, just what the heck is making
something like this. The most common feature on Europa are these ridges, and they come in pairs, these double ridges that's going up and then into the center and then up again and down. Light's coming from this way, from the right. I think the best model for this is kind of like a tree root growing beneath an asphalt sidewalk and pushing it upward to make a double ridge and break the cold, brittle ice on Europa. And it may be because that stretching creates cracks, and then those cracks, there's movement back and forth, and that back and forth movement creates heat, and that warm ice wants to rise up like a tree root beneath a sidewalk. That's, I think, a good way to explain these ridges, but there's no scientific consensus actually as to how these form. They may relate to water welling up from the interior. They may relate to compression, pushing together the surface. So there are a lot of different ways scientists have thought of to explain these ridges, and really going there and understanding the geological relationships close up, and even understanding the 3D nature of the subsurface is going to tell us how these form. And we'll talk a little bit about how to do that. Well, one of the things I could say here is that the Galileo mission was very limited. Its antenna didn't open. It sent back its data at 40 bits per second through a secondary antenna the size of a coffee can lid. The older folks in the crowd will know what a coffee can lid. And so we don't have a lot of the surface covered. With the upcoming mission, we're going to get all of the surface covered at 50 to 100 meters per pixel imaging resolution. There are also these things that are called bands. This one's a sickle-shaped one across the surface of Europa. And if you look at the older structures, the things it cuts, you can imagine, and there's this thing up here that's kind of funny looking, and then this down here is kind of funny looking, and this ridge, they'd fit back together if in Photoshop you cut this thing out and push the edges back together. And, well, we've done that. Photoshop is our friend in planetary science. There it is. So here, that's what that used to look like, and that, and that. And a crack came and split the surface, and the surface pulled apart somehow to form these bands. Here, a colleague illustrated this version. This probably took 10 million years to happen, but this is an idea of how these bands opened up. So something is pulling apart the crust and allowing warmer material to ooze out. Some have argued it's water. I think it's more likely that warm glacial flowing ice oozed out over something like 10 million years. So it's kind of like plate tectonics that we have on the Earth, where there are areas where the surface is pulled apart. And just recently, there was a paper that describes some evidence of a place where the surface seems to have pushed together, and there might be something like subduction zones where, like on Earth, one plate dives beneath another. Very cool geology, but we need to understand more, and what are the implications for water, and where is there water? What's the role of water in creating these features? There are some impacts. This is that one with the bright rays. It's a Welsh name, Pwyll, we know it by, but Pwll, I can't really pronounce my Welsh, is what it's named for. But it still doesn't look like a crater on the moon because it's very shallow. It formed into something relatively warm, like poking a warm cake, it rebounded back up. That's about 20 kilometers across. And then you go to bigger structures. There are only 2 of these, and they kind of look like bullseyes. So this is a place where you'd expect a big crater, but instead there are these rings. And what probably happened is that the impact was large enough to punch through the crater that formed, punched through the entire icy shell. And water raced in, and the crater filled in with ice and slush and pulled into the center to break the surface in these concentric rings. So again, only 2 of these, and it suggests that these impacts penetrated through an ice shell about 20 kilometers thick, 13 miles thick. But that stuff in the center probably came from down in that ocean. we saw a lot of reddish looking things. Wherever the surface of Europa has been breached in some way, there seems to be this reddish stuff. What I suspect is going on is that the bright icy stuff surrounding it is probably just a thin coating. And if you went to Europa and dusted it off, you'd probably see this dark stuff. So what is this dark reddish stuff? Well, we're not so sure. We can look at the spectral fingerprints, the fingerprints of light reflected off of Europa's surface. People do this from Earth using Earth-based telescopes or Hubble telescope. And with the Galileo mission, we were able to do it from flybys. And with the upcoming mission, we'll do it even better with flybys and other techniques. The idea here is we're looking at reflection off the surface in near infrared wavelengths, right? Beyond the color red, where our eyes can't see, longer wavelengths. And we can look at how much light is reflected off the surface versus the wavelength. We can see down in here, but not out here. So this blue curve is what ice looks like. There are these very characteristic dips. I don't do this for a living, but good friends and colleagues who do, and they're like, oh yeah, that's water ice, right? Because they know there's this dip right here at 1.5 microns, micrometers, and another at 2. And then they'll look at this and say, oh, well, there's water in there, but that's not water ice, because they're not as deep and they're somewhat asymmetric. They're just displaced for compare the shapes, not the vertical offset. And so what can make it that subtly different shape? Well, the best fits are magnesium sulfate hydrate. That's Epsom salt. If this stuff came from the ocean, that could be a pretty good place to take a bath. But the other good fit is sulfuric acid hydrate. That's battery acid, which is not a good place to take a bath. And the truth is probably somewhere in between. They're probably both of these things. What's probably going on is that there's stuff that's come from the interior and welled up to the surface and even flowed on the surface that contains Epsom salts. But once it gets to the surface, then Jupiter's radiation takes over. So I had that illustration of Jupiter's magnetic field. Jupiter's a giant particle accelerator. When there are charged particles out there, as there are, lots of them, because Io's a litter bug, and then things get, with its volcanoes, and then things get charged, ionized. And then they get accelerated by Jupiter. And they're whipping around. Jupiter's rotating every 10 hours. And these things are going around every 10 hours, even though they're really far from Jupiter. They're going at incredibly high velocities. And they're slamming into Europa. And that'll break apart H2O, water, into H, floats away, and O, which hangs around on the surface. And if there's magnesium sulfate hydrate, well, there'll be magnesium hanging around and sulfur, because all these things get broken up and can recombine. And some of it recombines probably to form battery acid. So that's a simple story, but it's probably not the real story. In other words, we need to understand better these little wiggles, because we could tell pretty precisely what's on the surface, what other salts are on the surface, and whether there are organic materials on the surface in this dark stuff, if we could see the finer wiggles in these curves. And if we had a more sensitive instrument with higher resolution, and that's what we'll have with the upcoming mission. The upcoming mission will also be able to catch tiny dust particles that are knocked off of Europa's surface and analyze them, and right there at the spacecraft, and say, oh, look, there's organics in here, right? Send us back the data. We'll say, look, there are organics in here. And there's also on board, there will be a mass spectrometer that will sniff the atmosphere. It's a very thin atmosphere around Europa. It's 10 to the minus 12 of Earth's atmosphere. And look for the gases, and that includes volatile organics that might be out there, and tell very precisely what chemicals are down, what's the chemistry of this dark stuff on the surface. By the way, neither magnesium sulfate nor battery acid is red. A recent idea is that it might be table salt, NaCl. when you irradiate it in the lab, turns this kind of brownish color. So that's an interesting idea, and there is some evidence for sodium at Europa. So we need to understand the chemistry to really get at the habitability of the ocean. What is the interior of the ocean like? What's its composition like? And to understand what part of it is from external factors. And keep in mind that oxygen that I mentioned breaking apart, because that's going to be a key part of the story coming up. If we look at the surface, we see these spots and pits littering the surface. They're called lenticulae, Latin for freckles. I have to give them a fancy name. There's something like 5-10 kilometers across. They're sort of rounded. They commonly occur together. And as a geologist, I knew when these pictures first came back, I've seen that somewhere before. And the somewhere is places like, well, I've seen it in books, but places like the Gulf of Mexico where there is salt that moves up from below sediment and comes and pops its way up through the sediments. Well, that's probably not exactly what's happening on Europa, but something close to it. It's probably ice, warm ice, rising up from the base of the ice shell like a lava lamp. Again, I'm showing my age, so older ones in the crowd. No lava lamps. The tidal heat we talked about is best, there's the most tidal heat down near the base of the ice shell where the ice is warmest. And so this warm ice wants to rise up through colder ice. And so you get these blobs moving up. Here's a simulation done by Amy Barr back when she was a grad student with me in Colorado many years ago. And in her model, the base of this is roughly the temperature of the ocean, of salty ocean, and the surface is frigid. So Europa's surface is 100 degrees Kelvin, that's minus 280 Fahrenheit, or if you like Celsius, minus 170 Celsius. So very cold and stiff ice. But the ice down here is kind of, it's warm enough to flow like glaciers flow. Ice flows over long time scales. This is way sped up. It'll be something like 100,000 years for ice down here to rise up toward to near the surface, but it probably happens over long time scales. And then the colder ice will sink down to replace it. So this is a way that Europa's ice shell may circulate. Stuff from the bottom, including any organisms if they're down there in the ocean, can get up to the surface, and stuff near the surface can get down into the ocean. Again, this is going to play a role as we talk about chemical energy here in just a few minutes. Oh, sorry, I didn't mention that, right, how do you get this stuff to the surface? So this warm ice isn't getting all the way up because it's so cold and so stiff. So if the surface is fractured, it might be able to make its way all the way up to the surface. There's one more major type of feature on Europa, and this one probably directly relates to liquid water, and that's the aptly named chaos terrain, where blocks, big iceberg-like blocks, have moved around, rotated, translated in this more hamburger-like stuff, kind of like I showed early on. So something has caused the surface to break up. Some heat source from below has probably caused the surface to break up for features to move around, right? Like this probably fit back together with that. These guys fit back together real well. This looks like it's tilted a bit. Something has disrupted the surface here. Let's take a look at this area, Connemara chaos, as it's called. From all the way out, let's zoom in. So that chaos region is here. I was in my office at Brown when we were planning the Galileo images when my friend Jeff called and said, Bob, we have to take pictures of the red rabbit. I'm like, Jeff, what are you talking about? The bunny. Here it is, the upside down bunny. And we did. We ended up retargeting images that were going to be taken somewhere else to this area, which even from a distance looked like it was going to be fascinating. And so we're going to zoom into various levels of Galileo data taken at different times during the mission to see this region revealed. So now you see these kind of plates that we were looking at earlier that broke apart. These bright areas are actually stuff that was tossed out of the crater Puch, 1,000 kilometers away. Zooming down now into images at about 55 meters per pixel show these rotated, twisted blocks. This is about the size of a small city. We used to compare it to Providence. This is about the size of an interstate highway. And then we'll zoom into some of the highest resolution images of the tour where Connemara chaos starts to become like a place, something like Monument Valley with plateaus and cliffs and stuff that has shed down off these cliffs. We're about 10 meters per pixel now. Whoops. Get rid of that little bar. And then we go out into the surroundings and see some of these iceberg-like regions. There's a ridge that's seen better days. That's about 1 kilometer across, if I remember. But the Titanic would be about that big for scale. But this doesn't look like a smooth skating pond like it was liquid water, but certainly liquid water is needed to allow these blocks to move around as much as they have here. So is this literally an exposure of the ocean, or maybe some of these blobs of warm ice have risen up and kind of like on a mosh pit that move the surface around? Crowd surfing. I always get that wrong. That's what it is. Well, one of the best models was a relatively recent one that kind of combines the idea that there's melting and that there's this convection, this warm ice that's bubbled up from below. That if there's these blobs of warm ice are places where tidal heating will concentrate. Because they're warm and they're rising up, that ice is squishier than the colder ice surrounding. So that squishy ice can heat up more to the point that there's melting right within the ice shell, creating a pocket of melt. And if there's a pocket of melt, the surface above could just collapse into it, and then it refreezes again later. So that's a nice model for how these chaos regions might form. It's pretty tough to get liquid water exposed to space at Europa with 100 Kelvin at the surface, but for short amounts of time, it is possible that there could be bubbling and frothing. Remember, there's a vacuum that will go right to a solid. Which leads into a relatively recent finding from the Hubble Space Telescope. The tantalizing evidence for plumes at Europa. Those familiar with Saturn and Enceladus is a very active moon orbiting Saturn, and it has plumes of water vapor that are spewing out of it. Well, the Hubble Space Telescope in the ultraviolet found some bright regions on the limb of Europa from a few years ago. And it's oxygen and it's hydrogen that's glowing there at the limb of Europa. And so that could mean that there was some sort of outburst, and then the radiation comes along and breaks it up into O and H, and maybe that's what we were seeing. But then NASA was intrigued by this idea and gave lots of Hubble telescope time to the group that found this, and they looked for months and months and never saw it again. So was this a big outburst and could only be seen once? Was the result not really right because it's a really hard observation to make? We're not sure. So as we plan our mission, we're planning for the possibility there might be plumes. We want to look and see if we can spot them. And then if they're there, we want to fly through them. Because if we're measuring the composition of the dust and the gas around Europa and fly through one of these, we could directly sample what's in the subsurface of Europa by flying through a plume, which would be just fantastic. So we have an ultraviolet instrument on the mission, our plume hunter, to go after whether there are plumes at Europa. So to sum up the ingredients for life: water, much more than all of the Earth's oceans combined. Essential elements, well, we saw this dark reddish stuff. We don't know if there are organics there. We don't really know the composition yet. We have to find out. Really, we know number one. Number two, well, we have ideas. We don't know. We need to keep exploring and get there and find out. But one would think that from Europa's formation and from later impacts bringing the right materials to Europa, that it should probably be there. The right elements to build organic molecules: carbon, hydrogen, oxygen, phosphorus, nitrogen, sulfur. Chemical energy is a hard one. So what we're talking about again is could there be enough energy for life down here in the ocean? Because you're not going to get sunlight, you're not going to get photosynthesis going on down beneath 20 kilometers of ice. For that matter, light penetrates, not too far into ice. Well, on Earth, there are lots of organisms that don't care about sunlight. They live off other chemical reactions. These guys don't care about sunlight. They live off the chemical energy from these black smokers on the Earth's ocean floors, places where water has seeped through cracks and pores in the rock and hit places in the rocky interior, not too far down, where warm rock is welling up. And that water gets charged with chemical nutrients, comes back out into the cold water, and those chemical nutrients just condense out. And these critters live very close to such things. So could there be the chemical energy for life at Europa? Well, in Europa's seafloor, there might be very similar chemical energy pouring out of the subsurface. And we've got another source too. The H2O here getting bombarded by radiation, breaking up into H and O, leaving the oxygen behind. If all the oxygen and other oxidants on Europa's surface could be dumped into Europa's ocean would be more oxygenated than Earth's oceans are. So there's the potential for lots of fuel for life at Europa's surface that could if it can get into the ocean. So the circulation of Europa's ice shell, like that convection we talked about, or like melting to form these chaos regions, is really critical. Understanding what's going on inside the ice shell to the idea of whether there could be life at Europa. Can we get those oxidants, the fuel for life, into Europa's ocean? Because if we just have the other part of the reaction, the reductants, not good enough. We need both sides of the battery. So the mission we're talking about carries an ice-penetrating radar. At long wavelengths, and Bruce Campbell is part of that radar team. At long wavelengths, ice is pretty transparent to a radar signal. It can go right through cold, clean ice, and if it hits liquid water, it's going to bounce back through that ice and back up to the spacecraft. So we're going to carry a radar that will broadcast at Europa and then listen to what comes back. And we're going to be plumbing the ice shell, trying to understand where there is liquid water within. That radar will penetrate at least a few kilometers. The hope is it could penetrate all the way through the ice shell as well. As for stable environment, Europa's probably been simmering, tidally heated for billions of years. We don't know that for sure. Further understanding of the evolution of the Galilean satellites as a whole will hopefully tell us that. So this leads into the goals and objectives for the Europa mission. I'm going to have to speed through a little bit. I have some cool graphics, so give me the hook when you need to. Overall, we want to understand the ocean, the ice shell, its composition, its geology. We also want to understand what the surface looks like close up, because someday after this mission, maybe soon after this mission, we want to send a lander to the surface. Because if you want to go beyond habitability, beyond understanding, could Europa have life, you want to go touch the surface, sample that stuff, get beneath the layer where radiation has messed stuff up, and scoop some of that stuff up from tens of centimeters below the surface, and look for signs of life. So before we can do that, we need to understand the surface, where we want to go scientifically, and how rough is it? Are there places we can land that are smooth? This is the best Galileo picture of Europa, 6 meters per pixel, somewhat oblique, like you're looking out an airplane window, and boy, that looks like a tough place to land. But that's what the JPL engineers are studying right now, whether we could send a lander to a place like this, or how. We know we could do it. This is our labeled version of our spacecraft. Here are, well, first of all, it's solar. Here are the solar panels. Each of these 8 panels is about 2 by 4 meters in size. Let's see, radio antenna for communicating with Earth, magnetometer boom. These are the radar antennas. There are high frequency antennas, 2 of them, each 16 meters long, and VHF antennas, 4 of them, each about 2 meters long, that we plan to attach to the solar panels. The solar panels are essentially going to be part of the radar system. The instruments like the cameras and the spectrometers are looking down at the surface of Europa, while the instruments like the dust detector and the mass spectrometer that's looking for gases are pointing in the direction we're moving. So it's like they're here and looking down, and we're flying through this stuff that those instruments want to sense while looking down at what the cameras want to see. So that way all the instruments can work at the same time. If any of you are familiar with the Cassini spacecraft, the instruments are kind of bolted all over, and only a couple can work during any flyby of, say, Titan. At Saturn, we want all the instruments to work at the same time, both for the scientific synergy that brings, and because this is a nasty radiation environment. We don't want our spacecraft bathing in radiation while 2 instruments look. We want them all looking at the same time. I mentioned most of the instruments, so I won't dwell here, but I'll just name them quickly. I mentioned mass spectrometer, sniffs the gases, dust analyzer for the dust, magnetometer. A plasma instrument helps out the magnetometer in doing its job of understanding how salty and thick that ocean is. Ultraviolet to search for plumes. Camera system can get up to 0.5 meter per pixel images of the surface of Europa for reconnaissance and for understanding the surface close up. Infrared spectrometer, ice penetrating radar. Whoops, I forgot one. The thermal imager is going to look for hot spots. Are there places that are warm enough at Europa that they're essentially glowing hot and we can detect that heat? It's the telecommunication system, the radio of the spacecraft, that does the gravity science that I mentioned earlier. There are a couple of ways to get to Europa. We can take an E-Vega trajectory, Earth, Venus, Earth, Earth, gravity assist. That's a lot of time spent in the inner solar system getting up enough energy to get out to Jupiter with the mass of this spacecraft. In fact, it would take 7.5 years. The launch period that we're shooting for, if budgets allow, and if NASA says to go in that direction, is May 2022. Is when the launch period would open. So that's the earliest we would be launching. So that's a conventional rocket, like an Atlas, a Delta IV, maybe the Falcon Heavy. But NASA is developing the SLS, the Space Launch System, a big, big rocket that we could take on a direct trajectory to Jupiter. And if it's ready in time, the time of flight to Jupiter is about 2.7 years, less than 3 years. That would be nice. As our project manager says, kind of my engineering peer equivalent at JPL, he hopes so because he wants to get there before he retires. So once we get there, then what happens? I've been talking about these tours and the pedals, the flybys, but what does that really mean? Here's a depiction of the spacecraft coming in. Here's the orbit of Europa. Jupiter's down the center there. And it's showing when we get first captured by Jupiter, a long orbit or pedal, and the beginning of the second. Well, let's look at this animated here. Once we make all these flybys, we're going to envelop Europa in a web of flybys here, I'll skip to that one. There it is from the side. We're going to envelop Europa with something like 45 flybys. This isn't an orbiter around Europa itself, but it's an orbiter around Jupiter. But every time it makes a flyby of Europa. And after 45, my Star Trek reference, we get kind of like a Tholian web formed around Europa, enveloping it, encasing it, and allowing us to sample all latitudes and longitudes around Europa. And see if I can get that to work. One last piece of the puzzle is that we are beginning studies, as I mentioned, of a possible lander. Not to join the Clipper mission, the Europa mission that we've been talking about, but to follow up soon after. And the idea is to try to get a few tens of kilograms of scientific instruments similar to Spirit and Opportunity's payload mass down to Europa's surface. And we're looking at trying to land something like this guy. And in doing so, use something like a mini sky crane, like was used at Mars, to help descend this little guy to the surface. That would be designed to be able to withstand a range of possible surface features, right? Europa might be very lumpy and hard to land on, or maybe we'll find some really nice smooth spots. But the goal is to get to the surface the kinds of instruments that could detect organic materials directly with big samples that are scooped out from the subsurface. So we'll see the results of these studies in the coming year or so. So to wrap up, Europa, first seen over 400 years ago, has the potential, exploration of Europa, has the potential to really revolutionize science in the coming decades. We have lots of examples of chemical reactions, and we have lots of examples of rocks, and we have lots of examples of other natural phenomena. We only have one real example of life to study. Biology is pretty much the same on Earth. All things are related in that there are 20 amino acids. Everything uses ATP to store energy. If we could find an example of life, of different life, life of an independent origin of Europa, it would revolutionize our understanding of biology. So that's a practical implication of finding life there. But beyond that, the question of are we alone is one that's been with us for a long time. It's one that sometimes we just assume it in science fiction, but we really don't know. How common is life out there in the universe? If we could find another example of life right here in our solar system, that would say that life is very common. And if it's not there, maybe it would say, hey, life is that much more rare than we thought. And the same place that revolutionized science 400 years ago, when following Galileo's observations, we realized there are other planets out there. We're not the center of the universe. That place, Europa, one of those moons that Galileo first saw and realized we're not the center of the universe, has the potential to revolutionize science again. So with that, I thank you, and we'll take some questions. Please see our website for more information. Yeah.
Beyond the ice, but in the water,
Oh.
like, is that even, that's the first theoretically possible? And as for the land mission, somebody thinking about possibly digging in the ice surface at mission to see it, like, is that even being thought about?
So I'll take those in turn. So the ice penetrating radar, if it sees to the ice, it's never going to make it all the way down to the ocean floor. It's going to be a challenge making it through 20 kilometers, 10 or 20 kilometers of ice if it's there, because it's difficult for ice penetrating radar to get through warm, dirty ice. And we think Europa's ice might be warm and dirty. It's easier for it to get through cold, clean ice. So what we're hoping for is regions, areas where it's cold and clean enough that it'll get all the way through to the ice, but it's not gonna, that signal won't make it beyond. As for lander, yes, there's definitely thought of, well, after an initial lander, then might we be able to someday get into the liquid water, whether it be a lake or all the way down into the ocean of Europa. So, but a lander would certainly want to at least dig beneath the depth that radiation has processed the surface. I'm going to attempt to restart as we're going.
There, yes.
When it comes down to tidal flexing, is it constantly increasing to make the ice get warmer, or is it just constantly increasing as it goes around?
So is tidal heating the same, or does it always increase? So very complex question. In other words, the answer is very complex. Well, maybe it's simple, we don't know. But where the ice is warmest is where we think the tidal heating will concentrate. And so where it's warmest may move around. You might have a big upwelling, and then the heat concentrates there to the point it melts. Melted water doesn't tidally heat, and so now it cools off, and maybe somewhere else it's heating up more. Now, that said, we think there may be a cycle on the order of 100 million years where Europa as a whole gets warmer and then cooler again. And this is because Io is thought to be in a cycle where its eccentricity, how oval that orbit is, changes over time. And Io pulls Europa along with it. It's an amazingly complex and interesting system. And so it's probably true that Europa has 100 million year cycles of being warmer and colder as related to Io getting warmer and colder in its orbit because of its orbit changing. The evidence seems to me to point to, and to other geologists, seems to point to we may be in a waning phase right now. We might have to wait around another 50, 100 million years before Europa really gets going again. So, yeah, absolutely right. There's not a lot of solar energy out there, but we're using solar panels. The Juno mission is paving the way. It's on the way to Jupiter, and it's using solar panels. What we did is we looked at the instruments that we thought NASA would select, and we said, yeah, we can power those with solar. And then NASA, in picking the instruments that were proposed, said to us, okay, can you accommodate these instruments if we pick something kind of like this? And we looked at it carefully and we said yes. As we're learning more, of course, we're learning that, oh, this instrument, oh yeah, we forgot to tell you we want to run for more of the orbit. Oh yeah, well, it's going to be harder to do the radar than we thought, or harder to do the mass spectrometer than we thought. So it's starting to push the system, but unlike a nuclear mission where your quanta, you'd have to add another entire RTG, or unit, to power the spacecraft, we can add more panels. And so originally we were thinking 3 panels on each side. We're up to 4 panels on each side going into the NASA selection. We might need a 5th. And so, but we can grow incrementally that way in cost and in mass, rather than adding another giant radiothermal unit, nuclear powered unit.
Way in the back corner up there.
The radioactive environment around Jupiter. So, silly question, ignoring the why or the how. Does the radioactive environment by itself make the idea of a manned mission a non-starter?
So does the radiation environment at Europa make it impossible to send people there? Again, I want to instill the use of crewed mission, although it sounds crude to use that term, but we don't have a good term for peopled mission. It is plausible. Remember, about a meter of ice will stop the radiation. So someday, people, I think, will visit Europa ultimately and make ice caves, essentially, right? If we want to explore Europa, we do it by finding or by building an ice cave, or by landing something on the surface massive enough that has enough shielding to be safe. Now, are people able to wander around on the surface of Europa? There would need to be either lots of shielding or some sort of magnetic shielding, right? And so then we get back into the science fiction realm, but it is plausible to have some sort of magnetic field enveloping astronauts in the distant future that would deflect the radiation particles.
Right here in the center.
What happens to the molecules that come out? What happens to the atmosphere? Is it an active atmosphere because it's become very hard because of that stuff?
So essentially, why doesn't Europa have an atmosphere today? It may have had one in the past. It's a small moon, not a lot of gravity, so like Earth's moon, molecules are lost to space over time just because the gravity is low, and so the particles will drift away. But also in this radiation environment, the stuff just gets stripped off very quickly. So if there are plumes at Europa, those particles will be dissociated. Oh, I think my computer's died. This is really sad. I was trying to show the movie, and now it's really unhappy. So the particles will get stripped away. Oh, man. I'm going to be on the phone with JPL tomorrow morning, I see. Let me stop there. If there are plumes today, some of that stuff will just freeze to the ground, and some of it, will be dissociated and stripped away.
Is there evidence for aurora or rings around Jupiter resulting from some of these, quote, plumes?
Good point. Is there evidence for rings or related phenomena at Jupiter associated with plumes? Not really. So at Saturn, at Enceladus's orbit, there's the E-ring, and that's made from stuff spewing off Enceladus. Now, Enceladus has much, much less gravity than even Europa, so lots more can escape, right? So lots of stuff will fall to the ground. The particles will fall to the ground at Europa. At the same time, people have done calculations to say, based on what we don't see a lot of stuff there, you could limit how much plume activity there could really be. So I think it was something like only 10% of what Enceladus spews out is it plausible to have at Europa. So you can use. Aurora, I don't think will be associated with plumes. Ganymede has its own internal magnetic field, and there are aurorae at Ganymede associated with that. There might be faint glows at Europa. We have, when we get there, we'll look for them. Yes, there are some, but aurora imply concentrated at the poles. But there may be just glow associated with Europa's very thin atmosphere and any plumes if they're there.
Go ahead.
Right, is there Europa science coming from the Juno mission, which is going to Jupiter? It's really concentrating at Jupiter. I think there might be some very distant observations of Europa in the ultraviolet, but not a lot coming in terms of Europa science. That's really concentrated on the big guy.
In the era of shrinking budgets for NASA, why Europa as opposed to the others, Enceladus or Mars or somewhere else? Make the point for Europa as opposed to the other places.
Right. Why Europa instead of Enceladus or Mars? Well, it fortunately hasn't been a choice of Europa or Mars. If it were, that would be Europa Europa was losing, right? And I mentioned Congressman Culberson, who's ensured that we're going to explore Europa and continue to do Mars. As for Enceladus and Titan at Saturn, those are really important places to explore as well. Enceladus may be spewing its ocean water out into space. If there's life there, we might be able to sample it directly, though there are challenges in doing so. It's not easy. And Titan probably has an internal ocean, and it has lakes of ethane and methane on the surface. How cool is that? That maybe there's some sort of weird life there. So we want to do that too. And NASA is investigating an ocean worlds program that would allow for such a thing. So, I mean, I would advocate, if I had to choose, I would advocate for Europa because of the potential for the ingredients for life. So even though radiation is deadly to life on the surface, you die in something like 8 minutes to 8 hours. I think I did the math once at Europa. If you didn't have a suit, well, it's cold too. But that allows for those oxidants, those radiation products, right? That's actually a good thing for life that might exist within. Enceladus doesn't have that. And Enceladus might be going through a burst of activity now And it's not clear there's been enough time for life to get going in its ocean. We're still learning at Enceladus. So yeah, I hate having to choose among the children, you know. But I think John Culberson would like to add to that.
Clarify with critical people who are passionate about this. Make sure you know that current law requires NASA to fly this mission to Europa because they canceled it last decade. Current law requires that you go to the surface and land and test for life. And the reason is that the ocean's there, shielded by ice, an ocean that has been oxygenated for billions of years. That ocean that has been shielded from radiation, from asteroid impacts. There's almost certainly black smokers on the bottom. And Bob Ballard points out that the ocean chemistry on Earth was finally explained by the black smokers on the bottom of our ocean. You couldn't figure out the chemistry of the ocean did not match what was coming out of the rivers until Ballard discovered the black smokers, and all of a sudden the chemistry lined up perfectly. And Bob Ballard tells me that the entire volume of Earth's oceans circulates through the mid-ocean ridges every 4 to 6 million years. You gotta let that sink in for a minute. That's happening on Europa. So you've got an absolutely perfect environment, an oxygenated ocean, shielded from radiation and asteroids, that has all the chemical elements for life, the most likely place in our environment, in our neighborhood that we're gonna find life. NASA kept canceling it, so I wrote it into law. I'm chairman of the subcommittee to make sure we take care of NASA, the FBI. I made sure, I'm chairman of this committee, and let me tell you, this is the only mission it is illegal for NASA not to fly.
Yep. Did I tell you Congressman Culberson is an advocate of this mission?
SLS is a big flagship mission. Both of them, the lander and the orbiter. The biggest, best flagships you've ever flown.
Okay, we have time for one more question. Right center, way at the back.
We're going to be alive to see life discovered on another world.
Any idea where all the water came from?
Oh, where did the water come from in the first place? It's cold out there. There was lots of H2O, lots of water in the nebula from which the sun and the planets formed. And here in the inner solar system, that only some of it, only a little bit was able to stay around. Out there in the outer solar system, lots of it was able to stay around in the form of ice, and it wasn't burned off essentially and lost. So it was able to condense out there at Europa, and Ganymede and Callisto are about half ice and half rock. Farther from Jupiter, it was warm Jupiter, it was colder out there. And then you go further out in the solar system, Saturn, Uranus, etc., lots of ice. Ice is like rock out there and condensed out and stayed. And here in the inner solar system, lots of it was lost, didn't condense out, just because it was too warm. Thank you.